My name is Nick Gasky. I'm one of the architects here at Kaleido. With us, we have one of the founders and our head of protocol, Jim Zhang. He's a seminal expert on all things blockchain protocols, as well as a lot of the bleeding edge privacy techniques, such as what we're going to talk about today, zero knowledge proof. So Jim will take you kind of through the landscape of ZKPs, decompose some of the realities of how those different libraries work, talk through approaches of, how that can be implemented, on-chain for privacy, off-chain via verifiable credentials, and likely a handful of other approaches. So really, really lucky and excited to have Jim with us here today. He's been a very trusted colleague of mine for going on about 8 years now. So always glad to have Jim in the saddle. A few pieces of housekeeping before we jump into it. This is being live streamed. It's also being recorded. So you'll get the recording and give us about 24 hours and you'll get an email from our marketing cohort with any slides that are shared along with the recording. If you are interested in subjects like this or the Kaleido platform at large, we have dozens and dozens of different modules and utilities and core services. I'd encourage you to visit our YouTube page. Just search Kaleido Blockchain. You'll see a curated library of hundreds of videos, many of which have my ugly mug on them, but many of which also include Jim and some of our other engineers. You can use that as a resource for this call or for any subjects that you want to revisit. We do encourage folks to be interactive with this. This is a pretty esoteric subject, so don't be shy if there's questions. Use the Q&A, use the chat. If there's time at the end, we'll do an interactive Q&A. I'll do my best to answer, but we'll likely need Jim and his expertise to chime in on most of the questions. But in any event, don't be shy, and then we'll leave different ways you can get in touch with the two of us and the broader team as the call sort of wraps up. So again, thanks so much for taking time out of your day to learn about this really fascinating subject. And with that, I will turn it over to my colleague, Jim, to jump into the conversation.
Awesome. Thanks, Nate. Hi, everybody. This is Jim. Very excited to talk to you guys about this fascinating subject. Would like to share with you guys our homework we've been doing in this zero knowledge proof area, since our customers have been asking us more and more to do support and enablement in this area. So we'd like to share with you our understanding of this area. Hopefully, there's just enough math in the explanation that is not so esoteric, using Nick's words, to scare people away, but enough to show that this is fundamentally a very well-crafted technology and very useful for all kinds of scenarios. Okay, so we'll first use some real-world, quote-unquote, real-world examples to demonstrate the idea of zero knowledge and how to prove with zero knowledge. And then the focus of today's session will be on the construction of one of the most popular ways to perform zero knowledge proof, which is using ZK SNARK. And then we'll just talk a little bit about what are the use cases that you can use zero knowledge proof for. And finally, some links for you guys to peruse afterwards to get more knowledge. Okay. So you may have heard of this if you look into anything about zero knowledge proof, the Sudoku challenge. This is a very useful kind of contrived scenario, but very useful way to demonstrate the idea of zero knowledge and how a zero knowledge proof can be constructed, and even some technical aspect. It goes like this. There's the famous Alice and Bob. If you go into any papers talking about cryptography, you're likely going to meet Alice and Bob. So they have been working in this interesting relationship where Alice designs Sudoku puzzles, and then Bob tries to solve them. So there's this one day that Alice came to Bob and said, hey, I've got another great, very challenging puzzle that I'd like you to give it a try. So Bob said, well, before I dive into that, I need to know this really has a solution, because the last time you gave me a challenge, I wasted 5 days working on this just to realize there's no solution. I don't want to do that again. So the challenge for Alice is to show to Bob, this particular puzzle does have a solution, but she can't give the solution to Bob right away because that sort of defeats the purpose. So how does this work? So what Alice can do is she first will scramble the solution. So what you see on the screen on the left is the real solution. She will scramble it by mapping every number to a different number. For example, 1 in the solution becomes 9, 7 becomes 8, and 9 becomes 2, so on and so forth. And now she has this other solution. And she will sort of cover this up. So none of the numbers are shown to Bob. And then ask Bob, just pick any row or any square or any column, and I'll show you what the solution looks like. So Bob just randomly choose, okay, show me the middle column. Okay, so Alice disclosed that middle column, and indeed, all of the numbers are unique. So this shows a real solution, but of course we know this is not a real solution because the number had been scrambled. So Bob learned nothing from the fact that besides the numbers are unique, he learns nothing about the actual solution. So now let's do this again. Bob is saying, okay, maybe you just got lucky. Maybe that's the only column you had all unique numbers for. Let's try this a few more times. So Alice will do another set of mappings, this time to a different scramble mapping, and then present the board to Bob again. Now Bob, this time randomly chooses a different combination. So how about this row? And Alice disclosed that indeed all the numbers are unique. After a few times, Bob may be convinced that this board has a solution, but still Bob has one question. How do I know this is the solutions you'd be presenting are the solutions for the actual puzzle? So Alice says, no problem. Let me give you the scrambled numbers for the actual puzzle. So remember, this was the original puzzle, and this is the mapped puzzle. So Bob can still be convinced, okay, these numbers they're properly mapped to the original puzzle. So the solution you'd be presenting to me is the right one for the actual puzzle. So after these interactions, Bob can be fairly convinced that the puzzle that Alice designed does have a real solution, because otherwise, if Alice tries to cheat, the chance of her cheating and getting every challenge right is very low. So as you can see at this point, zero-knowledge proof, this type of zero-knowledge proof is a probabilistic proof. You can never be 100% sure. You can be sufficiently convinced that the chance to cheat and to meet the challenge is very, very low. So as long as it's low enough for your criteria, you can be convinced that the knowledge proof is legitimate. So let's start getting to some real constructions. First, we're going to look at a simple form of zero-knowledge proof, and this is not based on SNARK. In fact, if you are somewhat familiar with public key algorithm, you know, there's a public key that is cryptographically tied to the private key. And the process to demonstrate the possession of the private key is in fact a zero-knowledge proof. And this is how it goes. We're going to use a elliptic curve-based public key system to show this. So in the cryptography based on elliptic curve for public key signing, the private key is just a huge number. It's a large random number. And the public key is this. It's a constant, we call it the G, which is it's called a generator in elliptic curve cryptography term, raised to the power of A being the secret key, modulo P. And the result is the public key, and that's published to everybody as public knowledge. And to demonstrate that you have possession of the private key, there are some basic math that needs to be observed. First of all, G raised to the power of A times C equals to G raised to the power of A, and the result is raised to the power of C again. And that's equivalent to the public key raised to the power of C. Another useful math about this is G raised to the power of M plus K equals to G raised to the power of M times G raised to the power of K. So both of these are useful for demonstrating the zero-knowledge proof. So let's take a look. So basically, what Alice does is she will pick a random number, K, and then she will do G raised to the power of K modulo by P, and the result is H. Share the H with Bob. So H is calculated like this, and it's shared with Bob. We should point out that when G and A is both sufficiently large enough, it's computationally infeasible to reverse engineer from the public key back to the private key. So even though G itself, which is the base, is public knowledge, the result of this calculation is public knowledge, you can go back and figure out what A is because of the modulo calculation part. Essentially, you have to just try one number at a time. There's no solving this in calculation fashion because of the modulo. And that's what's making it computationally impossible. So H is shared with Bob. Bob then picks another random number C and share the C with Alice. Now Alice has to calculate A times C plus K. Remember, K is the number Alice picked. C is the number that Bob picked. Both are random numbers. A is secret knowledge that only Alice has. She has to calculate the number S. So she couldn't calculate S unless she knows A. And again, at this point, C and K are both quote unquote known to Bob. We know K is not known to Bob, but the product of K raised to the power of on G is known to Bob. So now Bob can validate that Alice must have known the value of A because he can validate G raised to the power of S being the public key raised to the power of C times H modulo by P. So Bob knows how to calculate this. And as a result, if this all matches, then Alice must have known the value of A. Otherwise, she couldn't have come up with the value of S. So this is how essentially public key based on cryptography works, based on elliptic curve works. So now let's get into the construction of SNARK. So today's topic is about deep dive, right? But to be honest, there are many, many different versions of a deep dive into zero knowledge. Today's version is, let's call it a 45 minutes version of deep dive. There can be a 2-day version of deep diving if you're diving deeper into math. There can be a 2-week version of deep dive, depending on how much math you're interested in. So what SNARK does is, the assumption is majority of the world's problems can be expressed in arithmetic circuits, meaning it's doing a whole bunch of calculations, right? Zeros and ones and twos and threes, and then pluses and minuses or multiplications. So computer is really good at decomposing a bigger problem into smaller calculations and circuits. So SNARK uses a circuit as an input. So it basically builds a model based on the circuit, and then we'll see how it leads into a series of numbers to prove that you have correctly done all the calculations on all the parts of the circuit. So that's sort of what SNARK is based on. It's based on the circuits, which expresses the computation itself. So what does a circuit look like? Think of a circuit as a series of calculations breaking down into the smallest unit of calculation, where you have 2 input wires and 1 output. So any sort of calculation can be kind of broken down into these smaller pieces, where you have 2 inputs and you have output, and operator is either plus or multiplications. So for example, to calculate A plus B times B times C, this calculation can be expressed in this circuit that we see on the screen here. So you have first gate. We're going to call every calculation a gate. So there's a plus gate that takes A and B and outputs here. And then there's another multiplication gate that takes B and C as input and outputs. The 2 outputs then becomes input to the last gate, which multiplies them to get the final result. So keeping this in mind, now we can take the next step. So in the construction of SNARK, the first step is decomposing whatever the problem you're trying to calculate into these circuits, so that every step in the circuit are these simple calculation gates. So now we need to figure out a system to kind of represent all the collection of the gates throughout the entire computation. Because only after we are able to do that, we'll be able to verify that all the calculations are done correctly. And that's essentially what zero knowledge proof does, is to prove that the Alice has done all the calculation correctly without cheating. So first step is we use this so-called rank 1 constraint system to represent these gates. So again, let's use an example. Y equals x raised to the power of 3 plus 2x plus 5. The way we do the calculation is in 4 steps. First, remember there's no exponential operator in the circuits. There's only multiplication. So x raised to the power of 3 has to be done in 2 steps. One is, the first one is x multiply x. Second step is multiply x again. And the output of the first step, we call it T1. the output of the second step, we call it Z. And then the next step is 2 times X plus Z, and we assign it to T2. Finally, T2 plus 5, we assign it to the final variable Y. So this expression can now be represented in these 4 steps or 4 gates. So we're not talking about R1CS system yet. Just using this example to, so now we can have our circuit and our gates. So now let's do the R1CS representation. The idea is we want to build what's so-called a witness expression, basically capturing all the state, all the steps and variables involved in all the calculations. And we can see that if we put all the variables involved in these 4 steps together, just line them up, we have these. First of all, we always have number 1 as the beginning. The second variable we encounter is X, and we usually put the final output as the next one, which is Y. And the intermediate variables we put next. And that's T1 and Z and T2. With these 6 variables or constants, we capture all the variables involved in the calculation. So now what we can do is using these collection of vectors, we can express the calculation done at each step. So how is this done? Step 1, we have output being T1 and input being X, another input being X. So you can see we have 0 here and 1 here. So what this vector, when it's multiplied with the witness, we get just 1. So the first input for step 1, we get X. We time this vector to the witness string or the witness expression, we get X again, everything else is 0. And for the output T1, let's check, everything else is 0, and 1 times T1, we have T1, everything else is 0. So using the three vectors plus the witness expression, we can express the calculation that was done in step 1 or gate 1. Using the same technique, we can express all the calculations and steps using these collection of vectors. And this is what we end up. This is called R1CS representation. So at this point, what we have done is decomposing a problem into a collection of arithmetic gates. And then we did another transformation to use this R1CS system, which is a collection of vectors, or you can call it a matrix, to represent all the calculation steps. Each step involves 2 inputs and 1 outputs. They're expressed as A, B, and C. Okay, so maybe let's, before we move on, let's do a quick check to see if the R1CS matrix is correct. Now we're gonna go back to the example. Instead of using 2x, we use 1x, so this is just x raised to the power 3 plus x plus 5 as our calculation expression. And let's say we know if the challenge is find a solution when px is 35, prove to me that you know the solution. So internally, we know 3 is the solution. We're gonna use 3 to plug into this witness expression and just line up all the numbers. Again, the first one being number 1, it's always number 1. Second is X. In this case, we put 3 here. That's the number we know. And the next one is Y, and that's 35, that's given. The next one we have to calculate, right? So this is T1. T1 is X times X, so we put 9 there. And this is Z. Z is times X again, we put 27 there. And this is T2. T2 is plus 5. What is T2? T2 is plus Z plus 2X. And we put 30 there. So this is our witness series. And if we apply this to our R1CS construction, do we have all the calculation checking out? Let's take a look. This vector applied to this, we get 3. This vector applied to this, we get 3. This vector applying to this, we get 9. This checks out. Left side is 3 times 3. Right side is C being 9. So this equals, so this expression holds. Second still holds. So you can check this. All the expression will hold when you multiply the vector with the witness string. So far, we're able to use our R1CS construction to represent our calculation, and all the steps can be verified as being done correctly. So what's the point of all this, right? We now have a way to check that all the calculations involved in solving our puzzle can be checked to be correct using the R1CS format. As long as you know the witness series, you can check that all the calculations are done properly. This is one way to check that you have done all the calculation correctly, but this makes the verifier's job pretty tedious and expensive, because the verifier has to do all the calculations that the prover did in order to verify. Is there a way to make the verifier's job a bit easier so that the provers may have performed 1 million steps of calculations, but maybe the verifiers can do the verifications in just 10 steps? So this is why we need to do the next level of transformation, which is to convert our complex matrix into polynomials. So why polynomials, right? Polynomials has 2 very important properties that are very useful for the construction of ZK SNARK. First of all, the coefficients on the polynomials can represent huge amount of information. And second, comparing the knowledge of polynomial is very simple. You don't have to validate all the coefficients. You just need to sort of pick a few random values on the polynomial, and as long as the resulting value is correct, you can be very convinced that this polynomial must be the right one. Because as we know, think of each polynomial corresponding to a curve. Even if you change the coefficient of a single coefficient of polynomial, the curve itself will change dramatically. And when a curve on a plot changes just a tiny bit, the way they can intersect is very small. So if you plug in a few random numbers along the x-axis, if all the y values check out, you know with a high level of confidence that the person doing the calculation knows the actual polynomial, matching all the coefficients. So this gives a way for the verifiers to not have to check that all the coefficients are correct, only to just plug in a few random values and ask for the resulting y value. Okay, so how do we do this next level of transformation? This is where things get pretty interesting or pretty gnarly. Okay, so on the screen, you have our original R1CS system, the matrix. What we do now is we slice them up vertically so that you get a series of polynomials. So what do we mean? You can see we want to construct our first polynomial as a degree of 3 going vertically so that we have four numbers represented. So as a result, we have our first polynomial being 0.833 x raised to the power of 3 and so on and so forth. So how do we come up with this? So what we need for this is, can we find a polynomial that when x is 1, the result is 0, when x is 2, result is 0, when x is 3, result is 0, but when x equals to 4, it gives us 5. And you end up with this polynomial. You can check. When you plug in x equals to 1 or 2 or 3, this polynomial gives you all zeros, just like this. But when you plug in 4, the result is 5, which is this. So using this polynomial, now we can represent these 4 numbers. And again, A2 is representing these 4 numbers. You can check that this polynomial gives you 1 when x equals to 1, 0 when x equals to 2, 1 when x equals to 3, 0 when x equals to 0. Exactly how you find these polynomials to give you these results, you can read from the tutorial linked at the end. We're not going to go into that details. But the result is for A, instead of 4 vectors of 6 elements, we have 6 polynomials of degree 4. So that's what we've got now. We have, in the end, we have 3 groups of polynomials. Each group has 6 of them. So that's the conversion we've just done. Okay, so then you ask, right? So with the R1CX, we have the constraint that for every row, A times B equals C has to check out. What's the constraint on these polynomials? The constraint is that when you plug in x1, 2, 3, 4, so y4, right? So this is how many steps are involved in the calculation or the number of gates involved. That's how many x you need to plug in. When you plug in x equals to 1, 2, 3, and 4, and so on and so forth, the polynomials have to give you the original R1CS numbers. So that's the constraint we have on these polynomials. So essentially, this conversion happened so that we kind of rotated our R1CS matrix from going horizontal to going vertical, and then we get a group of polynomials. In fact, 3 groups of polynomials for A and B and C to represent the same kind of circuit steps. So I see there are some questions. Maybe we can spend a minute to get to the questions. Nick, what do you think?
Yep, we can definitely do that, Jim. I think it looks like more than there actually are.
Maybe pick one or two. Yeah, we can get.
First one was just asking about the actual elliptic curve, or the signing algorithm that's used in the first portion of the demo. So maybe you can expand on the actual library underneath that.
So the specific curves that are friendly to zero-knowledge proof, there's BN 128, BLS. Some curves are more friendly to zero-knowledge than others, but elliptic curve, they sort of all follow the same same constraints. Just like ECDSA curves, seg P 256R1 K1, you all have the same constraints where when you raise the generator to the power of the private key and modulo the prime field, then you get the public key. So that's sort of the basic constraint. But these zero-knowledge friendly curves allows you to do these other calculations. We'll mention them later in terms of homomorphic hiding and pairing more easily.
Great.
Yep.
Thanks, Jim. And you're probably going to get to this on some of the later slides, but for developers, what would you say is the path of least resistance to actually start writing some code using these libraries, or crafting a super lightweight proof of concept? Any good starting points that you'd recommend?
Yeah, definitely we'll get to that. It's actually on one of our later slides to use the CirCom libraries and SNARK.js set of tool set to get started.
Awesome. Okay, let's pause the questions for now and keep cooking.
Sounds good. Hopefully we'll also leave some time at the end. Okay, so given we still have the same witness, and now we have these bunch of polynomials. How does the verification work? Remember back with R1CS, the verification works like this. You just plug in each of the vectors on each of the row with the witness series, and then you can do verifications. Very similar with the QAP sets of polynomials. We still have our witness, this exactly the same witness. That doesn't change with these transformations because those have to do with the circuit itself. And your input, of course. You still use that, and then you can still use this, we call it the dot product operator between the polynomials and your witness. And make sure that when you do A times B minus C, the result is a multiple of this special polynomial called Z, or zero polynomial, which gives you zero at all these X values. It's essentially X minus 1 times X minus 2 times X minus 3. The resulting polynomial is called the zero polynomial. This is where the calculation on polynomials is involved. We're not going to cover that now, but you can check it offline that the resulting polynomials do obey this constraint, and you can use the witness to check the verification. The verification in this step will guarantee that given the correct witness, given the correct sets of polynomials, which again is derived from the circuit, then this will hold. Okay, so let's see if we can do this verification. This chart sort of visualizes what we're doing. This series going vertically is our witness series, 1, 3, 5. So again, 1, 3, 35, going like this. So when we do the dot product operation, we will multiply 1 to this and 3 to this and 35 to this, and then add everything together. So I did the offline computation for you guys. You can see that when we perform this operation, the resulting polynomial becomes this. So this is compressing these group of 6 polynomials into a single one after we've applied the witness expression. And you do the same for the other group of polynomials. So now we have a B, and then we have a C. So now 3 groups of polynomials became 3 polynomials, A and B and C. Now, do they obey the constraint? Again, the constraint being this in the middle of the string. So now we need to do multiplications of polynomials. This is fun, right? So when you multiply this polynomial with this polynomial, the result is this. I did the calculation offline like this, and then minus C, right? Minus C, the result is this. So A times B minus C, we get this polynomial of the order of 6. Does this cleanly get divided by the 0 polynomial without any remainders? Well, let's take a look. The 0 polynomial in this case, since we have 4 gates, it's x minus 1 times x minus 2 times x minus 3 times x minus 4. And this is our 0 polynomial. So let's use our result from the previous step divided by our 0 polynomial. You can do the calculation and you will realize the result is a polynomial with no remainder. This is critical. If your calculation resulted in a remainder, that means your witness expression was not correct. Because the polynomials, the groups of polynomials are going to be correct because they're public information. They're derived directly from the circuit. So if you messed something up, that must have been your witness series. And that means you did not do your calculation or computation correctly. So essentially, having no remainder is the proof that your witness string is correct, meaning your calculation were all done correct. If you had remainder, then your calculation was not done correctly. So at this point, this is at the core of SNARK, is that an expression representation of the circuit can be validated using a witness, and that can be checked to see if all the calculations are done correctly. So again, let's review what's happening, right? So first of all, with all zero knowledge proofs, what's publicly known is the circuit itself. Everybody has to know what is the circuit. And then from the circuit, we do the transformations of R1CS first and then QAP next. We end up with the 3 groups of polynomials. How many are there in each group has to do with how many elements are in the witness expression. So those are public, and also the the zero polynomial itself is public because, again, it's constructed from how many steps or number of gates there are in the circuit, and then we know the zero polynomial. So those are public knowledge. What the prover needs to do, and essentially is trying to prove to the verifier, is the knowledge of the witness. But of course, the witness itself must be hidden because the witness is a direct result of applying the solution to the computation. So the prover keeps the witness private, and then using these verification steps will prove that the prover knows this a witness that meets this constraint, where after applying the witness to these sets of polynomials, we get A and B and C. And when you do A times B minus C, the result must be divisible by the zero polynomial. Once you are able to prove that, that's the convincing fact to the verifier that all of your calculation have been done correctly. Okay, so at this point, what we have gotten to is we figured out a way to transform the calculation into a system. We call it QAP, so that when we present these numbers, A, B, and C, these are polynomials, right? And H, the verifiers can check that you have knowledge of this witness series that must be compliant to the circuit, meaning that you've done all the calculations correctly. Again, the verifier doesn't have to do all that complex calculation. All it needs to do is to randomly pick even just one X number, we call it S, and then ask the prover to plug it into the prover's A and B and C and H, present the result, and then the verifier can verify the result. So without doing the polynomial verification, it just needs to be done to do a value verification. So, but there's a but. So essentially at this point, what we have introduced is a proving and verification system, but there's no zero knowledge yet. The zero knowledge comes because of the fact that Bob can't let Alice know what the secret S is. What's the secret X value that Bob is going to use to validate? And conversely, Alice don't want Bob to know what the actual polynomials are. So why should the X value be hidden? So this is why. If Alice knows what the X value is, the value that Bob will use to evaluate to decide if Alice has the right polynomials, then she can cheat. So using the example, right? Let's say the statement Alice is trying to prove is that she has 1,000 in her account. And that resulted in this polynomial, on the top. But Alice, in fact, only has 900 in her account, and that resulted in this polynomial above. If Alice knows that there's the number Bob is trying to pick, she knows the value, the Y value, when this is evaluated against the proper polynomial. Then she can tweak, this polynomial so that it also gives the same Y value on this S. So even though these are completely different polynomials, they give the same Y value on S. So if Alice knows this evaluation point, she can cheat this way pretty easily. So that's why Bob has to keep this evaluation point secret from Alice. So how does that work, right? I need to ask Alice, please evaluate your polynomials on this X value, but I'm not going to tell you the X value. How does that work? So this is where the same technique that public key system uses applies here. So we're going to essentially encrypt our evaluation point by raising that on the generator value on the curve. So we pick the S. Instead of giving Alice the S, we give Alice the value G raised to the power of S modulo P. So that way Alice can use it to do calculation, to do the necessary calculation. We don't have time to go into the details without knowing what S is. So all the calculation still holds, even though Alice doesn't know the value itself, because of the logarithm exponential operations. Okay, so, and there's another step, the final step to make it non-interactive. So we generate a common reference string. Don't really have time to get into that. So we need to wrap up. So the kind of scenarios that you can use ZKP for, we already said public key signature, that's one scenario. If you want to hide transaction payloads in blockchain, so Jim has $1,000 and is transferring 10 to Nick. This is a transaction, right? If you send it to Ethereum, everybody knows your balance and how much you're transferring to Nick. If you want to hide all that, you can do this transaction off-chain and then give the transaction payload itself to the blockchain in the form of zero-knowledge proof, so that all the nodes in the blockchain can validate that this proof represents correct calculations, but nobody knows what is the input to the calculation. So Zcash or Nightfall confidential token, it's applying this technique. It's also good for scalability, not necessarily for privacy. So Ethereum is, layer 2 is very important for Ethereum or other public chains. All the layer 2s wants to prove that all the calculations done in their EVM in their own layer are done properly. And that is done through zero-knowledge proof. It's a proof saying that all the calculations I've done in my layer 2 EVMs were all correctly done without cheating. And that's a zero-knowledge proof, a very concise and small proof to represent a huge amount of computation. So that's very useful in that sense. Finally, in self-sovereign identities or decentralized identities, oftentimes you don't want to disclose your information, but you just want to disclose a proof that your information you hold meets certain criteria. For example, when you show up at the bar, you need to prove you're over 22, but you don't want to disclose your exact birth date. So you can generate a proof that says my birth date is before a certain date, showing that you are over 21 with a zero-knowledge proof. And finally, this is where you can find more information, specifically the circuit compiler, the CirCom, and SNARK.js on the bottom of the screen. Those are really good toolkits that you can use to get started constructing your simple zero-knowledge proof circuits, compile it, and then use the SNARK.js library to exercise some proving and verification. All right, so I think we better get to some questions before we really run out of time.
That's really great. Thanks so much, Jim. I'd also point people to Kaleido's public GitHub repository, just kaleido.io. You can kind of marry that CIRCOM compiler and the SNARK library with the IDEN3 stack. So you can go full circle and get all the way to seeing a verifiable credential, creating DIDs, and actually like issuing a challenge, a ZK query, and generating that proof. It's really, really cool stuff. Probably only time for one or two questions, Jim. See a few here on folks interested around the sort of computational lift for creating some of these proofs, and whether it would be prohibitive towards certain types of use cases like machine learning. So I wonder if you could maybe spend a few more minutes talking about how much is really happening, like with the generation of the proof, with the verification of the proof, and whether it is in fact prohibitive to certain sort of integrations or touch points.
Yeah, sure. That's a great question. The proof time, right? That's sort of the limiting factor in all of this. Verification, as you can see, is very straightforward. The proving time is pretty much linear to how complex the circuit itself is. The rest of it is pretty constant in terms of the time it spans. The more complex the circuits, the bigger the polynomials, and the longer the witness string. So if your computation is, the number of steps it takes is in the millions, proving time is going to be fairly long. I think ZK EVM, if I remember correctly, the number of steps is in the tens of thousands, and the proving time, some of the slower circuits can be a few hours or even almost a day. Some more efficient ones can be a few hours. So that's kind of the time scale we're looking at.
Awesome. Thanks for that. I think you did a pretty good job of kind of addressing all the other questions. So I think we can call it a finish line today for this chat. I did, for the folks remaining on the call, I did put a few ways you can get in touch with the team here if you want to talk more about ZKPs or just talk about Web3 infrastructure in general. Kaleido has a ton of functionality, a ton of services, and a bunch of application accelerators that can really kickstart your journey in Web3, and also give you that final push to get it to proper enterprise grade. So please don't be shy to get in touch with us. We're open to conversations of all shapes and sizes. And then if anyone is attending Consensus 2023, today through Friday in Austin, please come find Kaleido. We'll be mulling around the Hyperledger booth and the Consensus with a Y booth and the Polygon booth and all of our different partners in the industry. So I'll be there with two of the other founders of the company. You'll have to catch Jim at a different event here in the near future, but we'd love to chat with you in person. So please come find us, and maybe we can get you a t-shirt. So thanks again, everyone, for taking time out of your day. This is recorded. You'll get the recording. It's also posted on our YouTube page. And if there's anything else we can help you with, please use one of those email addresses to get in touch with us. And please stay tuned as well for information about an upcoming Tech Tuesday. We'll aim to show you some really new bleeding edge developments in the Kaleido stack that are very, very exciting.